All right, good afternoon, everyone. My name is Mohit Garg, and today I'm going to present this paper, Microsecond Consensus for Microsecond Applications. So let's get started. So first of all, I guess the question is why do we need microsecond consensus? Uh, I mean, if we are developing consensus algorithms and developing applications that use consensus algorithms, it may seem that we talking about microsecond consensus is going a little too ahead of the curve. However, we see that the microsecond applications in some domains are already here. There are financial applications like high frequency trading, where millions of dollars are being spent to get an edge of even a few microseconds. Then you have embedded systems like industrial robots, and if you have microsecond latencies, you can get a very high response, which is important to get precise movements in these systems. And then you have the microservices architecture, where the composability of the services to form a single high performant application relies on the networking latencies being as low as possible. So applications of these sorts can definitely use consensus for replicating any critical state that they have. The thing is that our existing notion would tell us that consensus is supposed to be slow. So, uh, so fast applications can use replication for fast fault tolerance. However, if the applications are microsecond level, then the replication should be at the microsecond level as well. Otherwise, any performance gains in the application, any optimizations that you do in the code of the application would be negated by the replication layer. That being said, as soon as we want microsecond consensus, the TCP/IP stack immediately falls out of the picture, because the TCP stack requires at least hundreds of milliseconds of latency. However, we do have
It's
RDMA,
microseconds.
microseconds of latency. However, RDMA is a hardware solution which can give us a single-digit microsecond latency. Uh, Combined with the right algorithm, we can achieve microsecond consensus. And the contribution of the paper that we are talking about today is precisely that mu is the microsecond consensus algorithm that is discussed in this paper, and it is used for it is built for a data center setting. So it's not built for like any wide area network stuff like that. In the best case, with no failures, the replication time can be as slow as 1.3 microsecond. And I guess the more interesting part is that the failover time, if the leader fails, switching to a new leader, is under 1 millisecond. That is quite interesting. So let's quickly look at as a background. Let's look at RDMA. RDMA stands for Remote Direct Memory Access. So network communication is generally a two-party step. The sender sends some data, and the kernel, the networking stack determines, it examines that data, and depending upon the headers and stuff like that, it places it in a location in the RAM. The inclusion of the CPU and the kernel here adds latency, which can also dynamically change, right? And if you have a high load on your CPU, it is possible that your network latency may also go higher, as the CPU may start dropping packets if it's overly loaded. So that an equivalency could be that if the postman had to knock on our door and talk to us before delivering every piece of mail. So this is not what happens in real life. The postman just leaves the post in the mailbox without our involvement. This kind of direct access is what RDMA provides. So it bypasses the kernel and the CPU on the receiver side, and the sender can just directly place the data in the RAM on the receiver side. Due to this, it provides very high, very good latency, like in single digit microseconds, and it also provides very high throughput. So I think this number, the 100 gigabits per second, is something that RDMA provides in an InfiniBand setup. And an important characteristic of RDMA systems is that we have a mechanism to dynamically grant or revoke read, write access permissions. A sender which doesn't have the access to the memory, it doesn't have access permissions to the memory, cannot write to the memory of the receiver. So this is a primitive that is exploited or used in the paper to, to build the mu consensus algorithm. So now let's now start the discussion of the mu consensus algorithm. So let's first look at the roles that the servers play in the algorithm. So there is a leader which communicates with the clients, receives requests, and also replicates these requests to the followers. After the requests are replicated, the leader applies these changes to its local copy and responds to the client. There is a scenario where there could be multiple leaders in the system. However, the protocol does not explicitly prohibit that, but it tolerates these scenarios. The followers, on the other hand, are more or less passive. They don't communicate with the client. They passively receive replicate requests from the leader, and they apply these replicate requests to their local copy. And I guess the more important role is that they monitor the leader and are ready to take over if the leader is slow or has failed. So first, let's look at how the replication works. So in the common case, the leader receives a request from the client. The request is captured, and then the request is added to the log on the leader. So the authors have used this request capture as an abstraction, as they don't really care how they are actually capturing the request. It could be a function call that our client is making to the leader. It could be a socket connection, whatever. It doesn't matter to them. So to achieve as low latency as possible in the replication, the copy or the replication from leader to the follower has to happen in one round trip delay. So the leader basically copies the request to the followers using an RDMA write, and then the leader basically waits for an acknowledgement. This acknowledgement is a very low level RDMA primitive. It does not contain any protocol related, any protocol specific information. So there is, so if we are thinking of this in, like, if you are thinking of the consensus of the new consensus algorithm and are comparing it with Paxos based consensus algorithms, we might expect another stage, like another phase to this algorithm, but in mu there is only one step consensus. So this one round trip latency is what gives it like a very low, which helps it achieve very low latency. So to kind of think why we are able to do this in one step, so the rule that is exploited here is that only one server has the permission to write. Let's say P0 is the leader and it wants to write it to the P1's memory. It would ask for the permission. The permission is granted, and now P0 can go ahead and write to the memory of P1. Now, if P2 comes back and asks for the permission would be granted to P2, and P2 would be able to write to the memory of P1. So when P2 is asking for the permission, two things happen. Like P2 gets the permission, and also the write permissions of the P0 are revoked as well. So this is something different from our like Paxos algorithms. The permission is also revoked for P0. Now, if P0 comes and tries to write to P2, since its permission is revoked, it wouldn't be able to write. And as such, it would know that there is another leader running. On the flip side, however, if P0 is fast enough and is able to get the second write in, then that write would be successful. P0 would know that it is the only one writing since it got the permission, then the writes for P2 would succeed as well. So a simple permission management module is added to the consensus engine, which handles the permission requests and switches over permissions from one leader to another. The permission management module communicates using a separate RDMA connection or a queue pair. So that is a design idea so that the permission management, those requests are not interfering with the replication requests going on in the system. So I guess the more the replication is a kind of straightforward. However, I guess the more interesting part is the failover scenario. So mu follows a heartbeat-based failure detection algorithm. However, rather than sending out the heartbeat requests, it maintains a heartbeat counter for itself and reads the heartbeats for other remote nodes using RDMA. So, so it also assigns a badness score for other servers. So the badness score reflects the level of confidence a server has in detecting other servers' failure. If the heartbeat, so the every node is basically the followers are every node is basically monitoring the heartbeats on the other servers, and if the heartbeat stays the same, it increments the score. However, if the heartbeat changes, it decrements the score. So, and according to a given threshold which is set on these servers, the server is able to detect if the other node has failed. And again, sorry, my headphone just. Can you guys hear me fine?
Yeah, we can hear you.
Yeah, my headphones battery and so yeah, basically if the heartbeat remains the same, it increments the score. However, if the heartbeat changes, yeah, and according to a threshold, it is able to detect like if the other server has failed. And also, since the protocol tolerates a multiple leader scenario, so this failure detection system does not have to be like perfect. It doesn't. It's not reliant on having a single leader at all times. So finally, let's look at the evaluation. So the startup. So let's start with the setup. So the applications used for evaluation are Liquibook, which is a financial order matching application, Herd, which is an RDMA-based key value store, and Memcache and Redis, which are used as to compare against the TCP/IP-based counterparts. So the algorithms compared are all, the algorithms are APUS, DARE, Hermes, which are RDMA based replication algorithms. And of course we have mu. So all these applications are implemented using mu. However, the authors claim that due to the tight coupling between the consensus and the key value store layer, they haven't implemented the applications for DARE and Hermes, and they are just directly compared against the key value stores implemented in these algorithms. Uh, APUS is a socket-based
algorithm. So they have used it for Memcached and Redis. They used as a hardware setup, they used three servers as replicas and client server, which is connected by 100 gigabit InfiniBand connection to run the tests. So the first graph we are looking at is the latency graph. So uh, we have numbers for Herd, Liquidbook, Memcache, and Redis replicated using mu in the first four bars from the left. Then we have Dare and Hermes based key value store, and finally Redis and Memcache using APUS in the last two. So it's easy to say that the latencies for applications in mu are about 1 microsecond, and they are improvement of 4 to 5 times over the other algorithms. So that was sort of the previous one was an evaluation of the replication part of the algorithm. This is an examination of the failover time in the algorithm. So it is made up of two components. There is failure detection times and which are shown on the right, and we can see that they are all under 1 millisecond, like slightly under 1 millisecond. And the on the left we see the permission switch component of the failover time, and we see that it's around 250 microseconds. So we see that the permission switch microsecond forms almost quarter the failover time. And this is something that the authors say is really dependent on the hardware, and if they improve the hardware, they can of course improve the permission switch time, and the failover time of mu can also be improved as a consequence of that. Finally, let's look at the replication throughput. So they have compared the replication throughput by varying the batch size of the request, and also varying the number of outstanding requests. So as the batch size and the outstanding request increases, the throughput increases, but the latency increases as well. And the saturation is reached at about 45 operations per microsecond. And the authors basically allot this bottleneck to the copying of data of copying the request data from the client to the memory region on the server side, which is in use for RDMA. An interesting, maybe noticeable feature of this graph is that the increasing the number of outstanding requests with the same batch size increases the throughput considerably. And this effect seems to taper off starting with the 32 byte batch size requests. As we can see, when the throughput is around 29 operations per microsecond, if for two outstanding requests, if we increase it to if we increase the number of outstanding requests, the throughput increases to like 32 operations per microsecond. So that is interesting, I guess. Finally, I think the key takeaway from the paper is that the microsecond consensus is here. I think RDMAs, I didn't know much about RDMAs previously, and this paper was quite interesting in showing that how we can use it for various distributed systems applications for achieving very low latency. I think I'm a bit kind of suspicious about what would happen to the mu performance as we try to replicate larger requests, and how it would scale with the number of servers. But yeah, I think we can discuss it after the presentation. And with that, I think I'd conclude here, and yeah, we can start the discussion from here.